This presentation is as it pertains to functional limits and continuity. We're going to go ahead and define what a function is. So say we're given two sets A and B. We say that a function from A to B is nothing more than a rule or a mapping that takes each element x belonging to the domain A and associates with it a single element of the set B, which we call the codomain. In this case, we denote the function as f, okay, which maps an element from A to B. Given an element x belonging to the domain A, we say that the expression f of x represents the element of B that is associated or attached to that particular x belonging to A, right? And it's associated by that function f. The set A is known as the domain of f, and the range of f is not the set B in its entirety, but rather, I mean, it could be, but it's rather more precisely, it's the subset of B given by all such y elements or y values in the codomain B such that y is associated with some x in the domain A by the function f. What is a limit and an isolated point? Okay, these are important terms. Okay, so a point x is a limit point of a set A if every epsilon neighborhood of centered around x intersects the set A at some point other than x. Okay, so what this looks like is, say you have a set A, and we can note here very clearly that the leftmost point here is not a limit point because I can construct an epsilon neighborhood around it such that there's no intersection of that epsilon neighborhood with any point other than the point x. Now say I'm able to construct a sequence, okay, of terms that belong to A. And specifically, these terms are not my proposed limit point. Like, let's say this is my proposed limit point x. If I'm able to think about this in terms of sequences, and I'm able to show that this sequence of terms where each term belongs to the set A and is not the value, each term is not the limit point itself, okay? And if I'm able to show that that converges to x, what does that basically show? I mean, it basically shows that regardless of how small of an epsilon you choose, or in other words, how small of an epsilon neighborhood there is around x, okay, that at some point in that sequence there will be a term, and in the way we've created that sequence, it will be namely a term other than x that will enter that epsilon neighborhood. Okay, so that's kind of a way that we can show that x is a limit point, and that's basically what this next theorem gets into, okay? This theorem states that a point x is a limit point of a set A if and only if x is the point of convergence for some sequence that where each term in that sequence is an element of the set A and each term does not equal to the limit point, okay? So if you think about the forward direction of this, okay, what are we given? We're given that x is a limit point, okay? So if I can draw something where x is a limit point, and again, what does it mean for x to be a limit point? It means that regardless of how small of an epsilon neighborhood you choose, okay, regardless of how small of an epsilon number you choose, okay, that epsilon neighborhood centered around the limit point is going to contain some point other than x. Okay, we need to show that basically that there is some sequence um, of terms, okay, and each term belongs to the set A, and each term is not equal to the limit point, and basically that sequence is going to converge to x. Okay, so how are we going to construct this sequence? Okay, it's actually pretty intuitive. You want to start with um, picking a term from like a wide epsilon neighborhood, and then you kind of want to like build smaller and smaller epsilon neighborhoods around x. And so the way we're going to do this is we're going to pick, for example, the first term is going to be in the 1 over 1 neighborhood of x. And so we're just going to kind of pick, right? So that term right here is going to be our a sub 1. And then the next neighborhood is going to be the 1 over 2 neighborhood, right? And so this is going to be our a sub 2 term. Okay, and so the a sub nth term, okay, is going to be essentially in the which neighborhood? It's going to be in the 1 over n neighborhood of the um, limit point x, right? And we're going to pick it in a manner such that it's going to be something other than x. And we can do that. Why? Because x is it's a limit point, right? And by definition, each epsilon neighborhood, regardless of how wide or how small you choose it, okay, particularly how small you choose it, it's going to have a point other than x inside of it. Okay, so we're going to construct a sequence a sub n that each term is going to be, okay, the nth term is going to be in the 1 over n neighborhood of x, such that a sub n is not equal to the value x. And now we need to show that basically that this is going to converge, that this sequence is going to converge to x. Okay, so what we need to show is the existence. Well, first of all, we're going to let epsilon be bigger than 0, right? That's how you proceed with these kinds of proofs. And then we need to show the existence of a capital N such that whenever n is bigger than or equal to capital N, the absolute value of a sub n minus x is less than epsilon. That's basically what we need to show. What would imply this, okay, we know that the distance between a sub n and x, okay, it's always going to be smaller than, it's always going to be smaller than, I'm blanking. It's always going to be smaller than 1 over n, okay? And why do I know that? Well, if we think about it, each of these a sub n terms, right? They're in the 1 over n neighborhood, okay? A sub n is going to be in the 1 over n neighborhood centered around x. Okay, so if a sub n is in here, the distance between a sub n and x, it has to be smaller than it has to be smaller than 1 over n by definition, right? By definition, what does it mean for a sub n, right, to be in the 1 over n neighborhood of x? What that means is that um, a sub n is in the open interval, right, x minus 1 over n and x plus 1 over n, which in other words means that a sub n is in between x minus 1 over n and x plus 1 over n, right? Which basically means, okay, that the absolute value of a sub n minus x is smaller than 1 over n, right? Or the distance between a sub n and x is smaller than 1 over n, okay? So if 1 over n is smaller than epsilon, then that would imply that the absolute value of a sub n minus x is smaller than epsilon. Okay, well, when is this true? Well, n is bigger than or equal to capital N. So all we have to do is choose a capital N such that 1 over capital N is smaller than epsilon. And at that point, since n is bigger than or equal to capital N, 1 over small n will be smaller than or equal to 1 over capital N, which is smaller than epsilon. But we can do better than this. Okay, I want to be more precise with our choice of capital N. So what I'm going to do here is I'm going to take the reciprocal of 1 over capital N, and I'm going to flip this inequality symbol so that it's bigger than 1 over epsilon. What does that mean? It means throw at me any epsilon in the whole universe, regardless of how small it is. All I'm going to do is I'm going to take the reciprocal of your number, okay, and that's going to be the point at which all the terms will eventually fall into that epsilon neighborhood. Okay, will be epsilon uh, within x. Okay, but there is a slight problem here. Okay, is that sometimes if you give me an epsilon, 1 over epsilon may not be a natural number. So how do I be precise with my choice of capital N? I can't really say that it's going to be equal to, like, say for example 1 over epsilon plus some natural number 1. Okay, this is not going to work, right? What I can do, okay, is I can take 1 over epsilon. Okay, if it is a natural number, perfect. Okay, we'll keep it as it is. But if it's a decimal, what I'm going to do is I'm just going to round it up to the next highest natural number. right, to the natural number above it. I'm basically going to take the ceiling of 1 over epsilon, and so that's going to be my choice. Okay, so at this point, what happens is that when n is bigger than or equal to capital N, right, and capital N is namely the ceiling of 1 over epsilon, absolute value of a sub n minus x is smaller than 1 over a sub n. Well, that's true for any n, right? And that's going to be smaller than or equal to, okay, and since n is small n is bigger than or equal to capital N, right? Uh, since n is since small n is bigger than or equal to capital N, what that means um, is that 1 over lowercase n is smaller than or equal to 1 over capital N, and capital N is namely the ceiling of 1 over epsilon. The ceiling of 1 over epsilon, it could be equal to 1 over epsilon, or it could be bigger, okay, which would make this fraction, 1 over the ceiling of 1 over epsilon, smaller than 1 over epsilon. Okay, so we can bound this guy above by 1 over epsilon, which is nothing more than epsilon. Okay, so that means that for whenever small n is bigger than or equal to the ceiling of 1 over epsilon, okay, this is always the case. Absolute value of a sub n minus x is smaller than whatever epsilon you throw at me. My definition of convergence, that means that the sequence a sub n converges to x. Okay, and again, how did we create this a sub n? A sub n is a sub n is in the 1 over n neighborhood of x such that a sub n is not equal to x, and I should note that a sub n is an element of A, right? So A sub n is contained in A, and A sub n is not equal to x for all n in the natural numbers. Okay, so that's the forward direction. Now, how do we proceed with the backwards direction? Let me go ahead and clear the annotations here. Okay. How do we proceed with the backwards direction? So suppose there exists a sequence, A sub n, contained in A, satisfying A sub n is not equal to x for all n in the natural numbers, and that A sub n converges to x. Well, then that's pretty straightforward. I mean, we just use the definition of convergence, right? That means for all epsilon bigger than 0, there's a point at which all the terms and at capital N, right, at a sub capital N, and all terms afterwards, right, implies that a sub n minus x, absolute value of that, is smaller than epsilon. What that means is that regardless of how small an epsilon you give me, okay, every single epsilon neighborhood centered around x is going to contain a point uh, a sub n, right? And we know each a sub n is not equal to x. Um, so it's going to have that point. Okay, and that means every single epsilon neighborhood is going to contain a point other than capital A. Um, and so basically that's the definition of a limit point, okay? And so we can conclude that x is a limit point of A. Okay, now why is the stipulation that a sub n is not equal to x? Why is this important? Okay, well, say we want to see if 2, okay, is a limit point of this set. Okay, let's say this is 3, this is 4, this is 1, and this is 0. Okay, can I construct always an epsilon neighborhood around 2 that will contain either 0, 1, 3, or 4? No, absolutely not. Okay, that's ridiculousness. Um, but what I can do, okay, is I can still create a sequence that converges to 2, right? I can namely create the stupid sequence, right, of this, and that converges to 2, okay? Um, and so here it doesn't really make sense to say that 2 is a limit point just because this sequence converges to 2. And so for that reason, um, we want to make sure that that the existence of a sequence that converges to our proposed limit point is a sequence where none of the terms, okay, we want to exclude the possibility of terms possibly being our proposed limit point, okay? So that's the limit point theorem. With that being said, if something is not a limit point, okay, meaning you can find an epsilon neighborhood centered around that point where no other point is inside of that epsilon neighborhood, we call that an isolated point. Okay, so a point A belonging to a set A is an isolated point of the set A if it is not a limit point of A. So an isolated point, by definition, is a point of the set, okay? We need to be cognizant and aware of the fact that a limit point of a set A is not necessarily belong to A, okay? It could belong to A, okay, but we can come up with many sequences of terms that belong to a set A that converge to something other than the set A.